Alright, question 4 is asking you to find y prime. Y prime is one type of notation of differentiation. You can also use this notation here, derivative of y with respect to x. Same thing as this, they're equivalent. It's just that this one you can't really tell what it's being differentiated with respect to. But in this problem you can see the only other variable is x, so we obviously are differentiated with respect to x. So let's begin the problem. Let's rewrite it. Rarely you're gonna get like a problem that's so simple. This one looks complicated. You're gonna have to manipulate it for sure. You see that there's a natural logarithm here, so you're obviously gonna have to use some sort of natural logarithm rules. So one of the rules, basic rules, is that ln of AB is equal to ln A plus ln of B. If we can apply that rule to here, we will get ln x cubed plus ln root x squared plus 1. The next step would be we'll go one term at a time. We'll call this y1, y2. So let's work with the first one. So we know the basic rules for differentiation of certain equations, like the derivative of ln x is equal to 1 over x. We know that. Derivative of ln of x cubed is not 1 over x cubed. It's not like that. You have to do something with this cube, and you're going to use a natural logarithm rule where ln of x cubed is the same as 3 ln x. So now you have it in the form of this form. You can differentiate it. Constant, you can bring it to the front of the differentiation and just differentiate ln x. So y1 prime would be 3 multiplied by the differentiation of ln x is 1 over x, so is equal to 3 over x. Now let's work with y2. This one is tricky as well. You do have an ln, and you do have a root here. It's always best to, when you're working with ln's, is to get rid of this root and make it into the power of a half, which is another basic rule. This is equivalent to root x squared plus 1. You do have to use something called the chain rule here, and let me explain to you what that is. So if you look at this y2 over here, it's actually a function inside another function. We have the function ln of x, and we also have the function x squared plus 1, which is inside the ln of x, so it would be inside this x. So we have a function g, which is the ln of x, and a function x squared plus 1. So we can write this, we can rewrite this y2 as f of g of x. So g of x is inside f of x is equal to ln x squared plus 1 to the half. You can further simplify this by applying the ln rule, bringing the half to the front. So f of g of x is equal to 1/2 ln x squared plus 1. So the derivative of a composite function, we call these composite functions, function inside a function, is equal to the derivative of the first function, and you leave the inside function alone, and you multiply it by the derivative of the inside function. So in this case, the derivative of our f of g of x, and this is a constant, you can leave it out front, The derivative of the first function, ln of x, is 1 over x. So 1/2 multiplied by 1 over x. But you leave the inside alone, so 1 over x squared plus 1 would be the derivative of f of g of x, of just f, the component. And you multiply by the derivative of the inside, g of x, which is 2x plus 1. So this whole term corresponds to this f of whatever's inside. Actually, no. Hold on. This term here corresponds to this whole thing here. We have the f prime, which is the ln, and whatever's inside, we leave it alone. So 1 over x squared plus 1, and this component here is this g prime of x. I hope you understand. It's kind of hard to explain, but we could just know how to do this. Eventually you'll just be like, you don't even need to do all this this stuff here. You'll just know that the derivative of this is easily 1 over x squared plus 1 times 2x plus 1 and multiply by half. It'll become automatic. Just do a bunch of chain rule examples. We're going to do another one right after this, and it will be like an automatic thing. You'll just catch it right away. So let's move on to part B. Alright, so part B is asking us to find y prime of y is equal to cos x cubed multiplied by tan x, all of it cubed. That's what that means there with the 3 over there. It means all of that term is cubed. So to differentiate this, we see that there's 2 terms being multiplied, so we got to use the product rule, which is, if you have 2 functions, f of x and g of x, d of the x is equal to the derivative of the first, we'll just call it f prime, times the second plus the first times the derivative of the second. So just memorize this. Derivative of the first times the second plus the first times the derivative of the second. Derivative of the first times the second plus the first times the derivative of the second. Alright, so let's apply that to here. Y prime is equal to the derivative of the first times the second plus the first times the derivative of the second. And this tan cubed x, you can just rewrite it as this. It's the same thing when the cube is not on the x. So derivative of cos x cubed, you gotta see that these are all chain rules. You gotta see that these are all chain rule problems. So we'll call this over here. Let's work with this cos x cubed here. See what it's a composite function. Let's see what's inside of it. We got 2 functions here, cosine of x, and x cubed itself is another function. So this is function f, and this is function g. So we got to use the chain rule, and let's differentiate cosine, and then multiply by the derivative of the second function. So the derivative of cosine is negative sine. Y prime of this would be negative sine. And you leave the inside alone, you don't do anything with it. And then you multiply by the derivative of the inside. And that's your answer for that term. So you take the derivative of the outside function, you leave the inside alone, and multiply by the derivative of the inside. Let's do the same with this tan x cubed over here. See what happens. Let's see what functions this is composed of. So we can see that this kind of looks like this, right? Where the x's are tan x. So to differentiate something like this, you end up getting you bring the 3 in front, and you subtract 1 from the exponent. So that's one function right here. This whole expression here, tan x all to the power of cubed, is the rule we're going to have to use is this one here. Bring the 3 to the front, subtract 1 from it, and then we also have the inside, which is just simply tan x by itself. So let's apply the chain rule here. We'll do the x cubed form derivative, which is we'll bring the 3 to the front, leave the inside alone, and subtract 1 from the exponent. And then you multiply by the derivative of the inside, and basic rules of differentiation state that the derivative of tan x squared, of just tan x, is secant squared x. It's in basic tables. Memorize this. So that our final answer will be this long expression here. We said that our derivative of cosine x was sine x cubed multiplied by 3x squared. Then we have the tan cubed x expression where we left it alone. And then we have plus cosine x cubed multiplied by, we'll just go under, multiplied by 3 tan x squared multiplied by secant squared x. That's our answer. We can simplify this further if you want, but it's okay. Looks pretty complicated, but I mean, it's really just a chain rule. So practice chain rule problems, and they're gonna come for sure. You gotta be able to spot the functions inside them. But we got 2 more problems here for this question, and it's again, find y prime of the following expression. Y is equal to e to the power of cosine x over 2x plus 3. So you see that this is a quotient, division. So we're gonna have to use the quotient rule, which is that if you have a function f of x and a function g of x, the derivative of f of x over g of x is equal to the lower function left alone times the derivative of the top function. We need some more space here. Let's just go over here. So the derivative d by dx of f over g is equal to the bottom function times the derivative of the top function minus the top function times the derivative of the low function, the bottom function, all over the bottom squared. So you can make sort of saying to memorize, so you don't forget this. So low means the bottom function. D, high, this is high, the top function, minus high, D, low. So low means the bottom function, H means the top function. Low, D, high, minus high, D, low, all over the bottom squared. It's kind of like the product rule, derivative of the first times the second plus the first times the derivative of the second. I took calculus like 5 years ago, guys. I still remember this stuff by heart. I didn't have to research nothing. I didn't have to look it up. I just still remember this. Low D high minus high D low, all over the bottom squared. Derivative of the first times the second plus the first times the derivative of the second. Quadratic equation, if you want, negative b plus or minus the square root of b squared minus 4ac all over 2a. You just remember this forever, guys. You use it so much. So that's that. So let's work on this derivative. The only derivative we have to do is this e cos to the power of x and this 2x plus 3. This is really easy. Let's work on the dx. And we're using the this notation, but whatever. I mean, I could write y prime instead here. d dx of e cosine x. This is the chain rule. I suggest you pause the video and figure out what the two functions are in this and how you would apply it. So I'll give you a minute to do that. This one is really not that bad. Let's just do a little refresher over here. If you have a function y is equal to the power of 2x, e to the power of 2x, dy dx is equal to, you bring the 2 to the front of the e and you multiply by the original function itself. Same concept here, except you have to just also take the derivative of this cosine x, because that's exactly what we did here. You take the derivative of the exponent, bring it to the front, multiply by the original function. So we'll take the derivative of the exponent, negative sine x, bring it to the front. Easy stuff. Multiply by the original function. There you go. That's that. And the other derivative we have to do is just 2x plus 3, and that's just 2, right? Just take the derivative of 2x is 2, and the constant goes to 0. So our final expression, I'll go back to y prime notation, is equal to negative sine x e to the power of cosine x multiplied by the original function minus e to the power of cosine x multiplied by 2, and let's go down a bit, all over the bottom squared 2x plus 3 squared. Not much you could do with this. This should be your final answer. Let's go on to part D. Alright, so you look at this one here, y is equal to e to the power of sine x squared. You actually got like three things going on here. You got the e to the power of something, you got the sine of x, and you've got the x squared. So you got like three things here. You're gonna have to do chain rules here to solve this problem. So the first one we know is that e to the power of 2x, it has a derivative of 2e to the 2x. So automatically we can apply that here, call this mumbo jumbo on the top sine x squared, we just call it x, and we know that, and we just assume it's like the 2x in the exponent. We can bring it down to the front and then multiply by the original function. But when we bring it down to the front, we take the derivative. So let's do that. Let's start with that. Let's take the derivative of e to the power of whatever's up there. So you'll take the derivative of sine x squared, but sine x squared itself is not just a simple derivation. It's itself. So you can't just you got to watch out here. So we have to take the derivative of sine x squared. How will we do that? This one here is also the chain rule itself. We got a function f here, we got a x squared itself. So it would be cosine x squared, leave the inside alone, and multiply by the derivative of the inside, which is the x squared. So now that we know this, we can just put it in the front over here for this expression here. So cosine x squared 2x, and you rewrite the original function x squared, and that's the answer, right? That's the derivative of e to the sine of x squared. Once again, we took the derivative of this and we brought it to the front, and the derivative of this was found here. It's a chain rule itself. Alright, now we move on to the more of the juicy stuff. Question 5 is using loose logarithmic differentiation to find y prime given that y is equal to x plus 1 to the power of x squared. I know it's small there, but I'll rewrite it here. Our function y is equal to x plus 1 to the power of x squared. So logarithmic differentiation, if you read the theory about it, it just means you take the ln of both sides and then you simplify and you take the derivative. So ln, you put on ln on both sides. If you do something to one side, you have to do it to the other side. X plus 1, power of x squared. Right. So now we just apply log rules to the right side. Leave the left side. Left side's pretty simple. We'll apply the logarithm rules. You can bring the x squared to the front of the ln. And now we see that the left side is simple and the right side is product rule. We got a term here and a term here. So we differentiate both sides to find y prime. So dy, so let's work with the left side. Derivative of the left side would be 1 over y. But this is implicit differentiation. Whenever you're doing an implicit differentiation, usually we derive with our x here, so we just do it and it's simple. But when you're going to have to derive the y in that same formula, when there's a y, you have to tack on an extra y prime here. So we'll show you in the next example where you're going to do an implicit differentiation example. So you just tack on an extra y prime, and then you do the derivative of the right side, which is the product rule. So like I said before, the derivative of the first times the second plus the first times the derivative of the second, derivative of the second, alright, so the derivative of, let's leave this here, we'll just call this y prime 1 over y is equal to derivative of the first, 2x, times the second. Okay, plus the first times the derivative of the second. We know that this one is chain rule, two functions, function 1, function 2. So derivative of the first function, so multiply by, and you leave the inside alone. So you won't put an x over here. The derivative of ln of x is 1 over x. The derivative of ln of x plus 1 is 1 over x plus 1. But you have to multiply by the derivative of the inside, which is 1. And this is the chain rule. And that's our answer. 2x ln x squared plus 1 plus x squared times 1 over x plus 1. We're not done yet. We have to just isolate for this y prime over here. So y prime is equal to, you multiply the both sides by y, and let me rewrite this. And that's what always going to happen in logarithmic differentiation. You're going to have to multiply at the end. You're going to have to just multiply both sides by the y. And we know that y was the original function we were given. We don't just write y, we have to write what was y. Y was given to us in the original problem. It's x plus 1 to the power of x squared. X plus 1 to the power of x squared. And that's our answer. Alright, so question 6 is saying use implicit differentiation to find dy dx over y prime at point 1, 2. So ignore this point 1, 2, that's usually the last step. So our function is x squared plus xy plus y squared. And I'll notice that usually when we, in the past problems, we've gotten only pretty much this form, y is equal to some function with x's in it. There's no Look at this one. Look at the mess here. We got an x's. We got another y over here. We got a y squared. You could try to isolate for y here and then solve it the usual way, but that's going to be quite complex because we have multiple y's here, and we're going to use a technique known as implicit differentiation. So implicit differentiation is you'll go term by term the whole equation and differentiate it with respect to x, dy dx of everything on both sides. But notice that when it comes to differentiating the y, whenever you have like this, what do? So just memorize these rules. The derivative of y with respect to x of y is just y prime. It's y prime. Anything else, anything more complicated, like y squared, for example, would be the normal derivative of any variable raised to the power of 2, which is just 2x. So if the derivative of x squared is 2x, the derivative of y squared is 2y. But when it's a y in there, you have to tack on an extra y prime, right? So the derivative of y with respect to x of y is y prime, and the derivative of y with respect to x of y squared is 2y, y prime. Say we have derivative of x of sine y. It would be the usual derivative, cosine y, but then you tack on, you multiply by another y prime. So keep that in mind. I don't know, sometimes you might be tricked and they give you a z instead of an x, and I don't know why it could be an a. Just keep track of what they're asking for. If they're asking, if they're going to ask you dz, dA, same thing, you're just going to make the a the implicit differentiation. You're going to do derivative of a with respect to x would be a prime, but most of the time they're going to give you in the terms of x and y, so don't worry about it too much. So let's go term by term here. So derivative of x squared is 2x. Change color. So if the x's, you differentiate them like normal. Here with the next term, we got a product rule. So the derivative of the first, which is x, the derivative of x is 1, times the second plus the first times the derivative of the second, and I said that the implicit differentiation dy dx of y is y prime. And that takes care of the second term. Our third term is 2y, so plus is y squared. So with the derivative of that will be 2y, and you tack on that extra y prime. And the derivative of 7 dy dx is just the usual 0. So now we have our equation with y primes in it. We just basically isolate for y prime. So we'll keep the y primes on one side and bring everything to the other side. So x y prime plus 2y y prime. Bring over the 2x, negative 2x. Bring over the y minus y. We can factor out the y prime here. X plus 2y. Oops, this equal sign should not be there, it should be a multiplication. Is equal to negative 2x minus y. And divide both sides by the x plus 2y to isolate. Minus y over x plus 2y. And now we can evaluate the function at the derivative at point 1 comma 2. So we'll plug in 1 for x, 1 and 2 for y, and in doing so we get y prime of 1 comma 2 is equal to negative 4 by 5.
Alright, now let's move on to the graph part of the exam. Things like tangent, extrema, all those fancy mumbo jumbo words, they come up here, but don't worry, it's pretty simple stuff, guys. So let's look at this problem here. We have our function f of x here, and it's asking us for part A to find the values, the x values, where the tangent to the function f of x is horizontal. What does that mean? All right, let's say we have a function that looks something like this, for example, and a tangent line is a line that just barely touches a point on a graph. So there's a tangent at every single point. I mean, literally, there's infinite tangents, because you can break this up into infinite small increments. So where is this tangent line horizontal? That'll happen at this point here. And this line is very important in calculus. I'm not going to go in depth, but to find this line, it's useful. So that's what they're asking for. What value of x is the tangent horizontal? And to find that, you guessed it, we have to take the derivative of this function. So let's go through it and see how it's done. So the derivative of f of x is, so the first term just goes to x squared. These are really simple derivatives. I'm not going to go explain how they're done. So these are our derivative here. Ignore the Facebook. So now to get these values, it's basically setting the derivative to 0. So setting it to 0 and solving for your x values. So these will give you these two values right here, that where the tangent is horizontal. I'm not saying that this function is this graph. It doesn't look like it, but the concept is there. So what we do here is we're gonna solve for x values. We're gonna factor out x, 1, x plus 1, and, well, hold on a second. If we factor this out, using your whatever quadratic formula, or no, you could just eyeball it, just looking at it, you know that the factors are x plus 2, x minus 1. Set it to 0, and you get your x values are -2 and 1. So these are called critical values in calculus. The zeros of a derivative are the critical values. And these critical values will also help you find the absolute extrema of the given function. The problem B is asking you to find the absolute extrema over the closed interval 0 to 2. Absolute extrema is the highest point of the function and the lowest point. So in order to do that, you're going to take these two values here, and you're going to take this closed interval 0 to 2. You're going to make a little table, and you're going to, of x values, you're going to list these points, -2, 1, and 0, the range of 0 to 2, in the increasing order in this table here. So -2, the next one is 0, the next one is 1, the next one is 2. So at this point, you're going to plug in each value into the original function, not the derivative, remember, just this function here, and see what you get. And the highest and lowest values you get out of those are your max and min. So when you plug in all these values, you'll find that for -2, you'll get 9.333. For 0, you'll get 6. For 1, you'll get 4.833. And for the last one, you'll get 6.667. So you look where your highest value is, and your lowest value, this is your max, and this is your min. And that is the answer to part B.